This is the second part of our series of mini lectures having a look at compilation. In this particular section we're going to break down the process of compilation that most, if not all, C++ compilers will go through and try to identify what these different sections are. There's benefit in doing this, and we'll really see that in the next talk, which looks at optimization. But okay, I mean, it's useful in and of its own regard simply to understand the different stages of compilation. But if we do understand that, then what it will mean is that we'll be able to write our code in a manner that the compiler, and in particular the optimizing stages of the compiler, will be able to better and more easily parse. What this means then is that the optimizer is going to be potentially more effective. And that's a good synergy then, where we write code that can be highly optimized on our behalf. So ultimately we sort of benefit from that. In terms of the different phases that we're concerned about here, go through lexical analysis, syntax analysis, then sort of intermediate code generation, then native code generation, and then the process of optimization, which we'll look at more really in the next lecture. But we'll have a look at each of these different phases, or different stages now. By way of how or what controls these, it's generally the parser. So parser, if you like, is the thing that's responsible for syntax analysis. So it embodies or holds the rules, or the rules of the languages. It knows that if something has been written correctly. And quite often it is at the heart. It drives the process. And it'll go to what's known as a scanner, or the lexical analysis, and will say, okay, give me some input from the user. So it could be a statement that the user has typed in. It's going to be up to the lexical analysis, the scanner's job then, to actually parse or source code, and to take a chunk of that to mostly get rid of the sort of string-based processor, turn it into some tokens, and to pass that off to the parser, the syntax analysis, which will then check to make sure that it is syntactically correct, that it is a valid, potentially executable line of code. Once the syntax analysis is complete and the parser says, yes, I'm happy with that, and then passes us off into a stage sort of known as intermediate code generation, which will turn it into something basically at machine code level, though not necessarily precisely targeted for the particular platform we're compiling for. But once we've got it down at machine code level, we have a chance then to put in a whole bunch of optimizations, and we may do some optimizations at that sort of very low intermediate level, then turn it into platform-specific machine code, something that runs on the platform that we're targeting for. And then after that, we may also apply some more optimizations specific for that particular target platform. But that's generally the series of steps that we will be considering and we'll go through within the compilation process. So we'll start off with lexical analysis first of all. So the scanner, its job is to use our source code, is to take our source code and to break it up into what's known as lexemes, or lexical tokens. So these, I mean, a lexeme could be one that holds a keyword or an argument for a method call. So an example here, we have a character string, the character 6 followed by the character 7 followed by the character 5. And what the parser could do is it could look at that and look at the surrounding context, and it would decide how it is going to interpret that particular string. Remember, this is just an array of characters, so the character 6, 7 and 5. And one way it could do this is to look at it and say, oh, that's a literal constant of type integer with a numerical attribute token of 675. So that's the job of the parsers, to try to process these. The output is just as what we mentioned there. So it would take that string, for example, of 3 characters, and turn it into a little clump of data. One that says what it is. It is a constant value. It's not a variable, it's a constant. It is an integer constant, and it has a numerical integer value of 675. Now that's good. So effectively, the parser then has taken the strings, the characters that we've typed in, and interpreted them and turned them into sort of a more meaningful a description of what it actually is and what values does it has. What it means then is that the processor, the parser, doesn't have to be bothered then about trying to understand or interpret the text that we've written. It can simply say, okay, here I've got a literal value, it's an integer. Depending on the surrounding instructions or other things about it, is that then syntactically valid? So parsing then, as we mentioned, job of the parser is to check that what we've written is actually correct. It adheres to the rules of whatever language it is, C++ in this particular case. Other than being a rule checker, the parser also tends to restructure the program into sort of a tree-like structure, so an abstract syntax tree, an AS tree. And it captures better, if you like, the flow, the control flow of the program. It also tends to express the program in this tree-like structure, which lends itself then to the process of optimization. And you can see an example of one on the screen where we might have, for example, something like a variable declaration. So this is what the parser's pulled out. It says, okay, here's an integer variable. It has the sort of notional descriptor of my variable. We're combining that then with a mathematical operator, a multiply operator. And then after that, we're sort of breaking down the different things that we're multiplying it by. So a literal expression, say a value of 3, and so on. So it gives a structure to our program. I mean, it's not a new structure, it's a structure that was inherent into what we written, or we actually created by way of doing our source code, but it expresses it in quite a convenient data structure then that other processes, most notably optimization, can have a chance to go through, to parse, to understand, to manipulate, potentially to change. So once the parser has decided, yes, it's valid, it passes off then a chunk. It's not necessarily the whole thing at this point, but it is a chunk, especially a meaty chunk, off to be turned into machine code. And this is where we can have different phases of sort of intermediate code generation, where it's turned into a quasi-machine code, very low level, but it may not be specifically the instruction set for the platform that we're compiling for. There's good reason for doing this. When we think about optimization, there's different types of optimizations. There's some that will broadly hold across a lot of different types of platforms, and there's some that may be specific to a particular platform. So if the platform you're running on has some particular machine instructions which enable you to maybe to stream a number of multiplications together, now you may have that on one platform, you may have it in another, but it's of benefit then to separate these platform-dependent and platform-independent optimizations out. So at the quasi-machine code level, the low level, we can run a whole host of largely sort of platform generic optimizations. Once we've done that, we can then turn it into the precise instruction set that we're compiling for, and then maybe after that run a further set of optimizations on that. The process optimization, we'll look at it in the next lecture, the next part of this series, but in essence, what we're concerned about, certainly at that sort of higher level of optimization, is looking at the AST, what the parsers produce in terms of the structure of our program, and parsing that, manipulating that, removing bits of that are not necessarily that effectively are just meaningless or functionality that has no benefit or return to the programmer. So that's one phase of code optimization. There are others in terms of using the sequence of instructions that are going to execute as fast as possible. So I give you some examples here of the types of manipulations that would get trimmed out or parsed or pruned from our AST. So this is, I'm going to show you a code here that's all sort of some redundant, at least in part. So let's say I have a method, and line 3, in fact lines 3 down to line 6, we're assigning things. So we might have an assignment of I plus 0. And most of the optimizing compilers, they would realize then that if you're adding on a literal value, an integer value of 0, it's a defunct, it's an irrelevant operation, so it would prune that. Likewise, we can also bet if we multiply something by 0, then the answer is always going to be 0. I can work out that I take away I, again, is going to be 0, or that 1 plus I plus 1 is going to be the same as 2 plus 1. Now, these are all things that a programmer might not put in, or in fact would be silly to put in. But there's different things here. You may have some method that the compiler is able to work out will always return a constant value within some context. So there are different types of trimming operations. This gives you a bit of a flavor for them. Some of the other things that it's capable of doing, you might have this set up here where we have created some sort of local variable, integer I. We're assigning it, but we're not doing anything else with it. So it's able to calculate this is just a wasted creation and assignment. Global is equal to 1, global is equal to 2, then we return global is equal to 3, never get to it, so it's removing redundant code. So effectively that would all get trimmed down as global is equal to 2. Now, they're all silly things. A programmer wouldn't put these in. But it gives you a bit of a feel for some of the opportunities that there are to trim the AST, remove redundant elements from it. And we'll see some of the more complex examples whereby these types of trimming operations may actually get to apply to our code that we write ourselves. So linkers then, once we have taken our particular CPP file and gone through the parser to intermediate to full code generation, and we've run our optimizer, we then have a chunk of code for that particular unit, and this is where then the linker kicks in. For the process of linking then, each of our CPP files, yes, we have a chunk of runnable code, but doesn't mean the whole thing is of yet runnable. So the other types of information you have along with that sort of compiled package is information about, well, what other libraries or resources does this thing need by way of enabling it to run. And that's information then for the linker, because it knows what it has to then pull together or bring into a coherent whole to make it into something that's executable. We're not really concerned with this. It's just really a bit of an aside on this. There is actually a good number of different types of tools that can come in at the linking stage. So things like disassemblers or other ones having a look at if there's a problem about understanding the memory that was created at this point. That sort of rich tool set that there is growing about because there's a number of fairly common object file formats, particularly within C++, so that if you are writing some linkage tool set, that as long as you adhere to a supported object format, then you can, if you like, attach your tool set in with a say, standard compiler that produces to some of these formats. You can see a list of them there, like OMF, object module format, ELF, executable, linkable format, things of that nature. Short aside now, just simply because in C++ there are lots of different types of compilers. Generally, you can talk about compiler, you're also sort of using it really through an IDE in a lot of cases, unless you're sort of running on a sort of Unix background. So just a little bit aside on this now. As mentioned, there are lots of different types of compilers. Visual C++ is one of the more popular ones, one we'll sort of end up using. When certainly in the PC side, if you're thinking about using a compiler, quite often it comes along and it's packaged up with an IDE, an integrated development environment. But it's important to understand that there's a whole host of different programs that are coming together to produce an editor for creating text, along with a compiler, along with a set of linkers, along with a set of debug tools, and all of these things taken together form a coherent whole. And a nice IDE will incorporate and combine all of these, But if you want, you can actually go down to the command line and you can call all these things individually, and there can be educational merit in going through that process to actually understand, if you like, the sequence of things that the IDE is sort of doing on your behalf. For IDEs, there's a common set of build options: compile, build all, run, execute, debug. One thing I want to flag up here is that the difference between debug and release mode. In debug mode, what the compiler does is it actually changes the code that you write. It inserts a lot of additional things. And these additional things basically give it the ability to track what the program's doing, if it falls over, to work out whereabouts it was. Generally, adding them in, they increase the size of the program, they slow the program down, but you do get out all of those nice debugging features, so they're very useful. Obviously, when you're creating the program, you run it in debug mode initially until you're happy and content that it's passed all of whatever form of testing you're using. When you release it, you turn it into and you build it in release mode. And what that does is it cuts all of that out, and then generally it runs it at full speed. So by way of key takeaway on this one here, I mean, we had a bit of a very brief overview of the different stages within the compilation process. Important thing to understand in this one is that, looking at the next lecture, the compiler's here to help us. Yes, it is enforcing the rules of the language to make sure something is executable, but the process of optimization in particular is one that will try to make our program run as fast as possible. And as we'll see in the next bit, we want to help the optimizer do its job to the best of its ability.